Oh, interesting. Okay, that's good to know too. Yeah. Yeah, I appreciate the feedback with the My Open Math. So some people message me, and so that is super appreciated. So again, if you're like even participating somewhat in that, you'll be on like what I call a different grading scale. And so that way all your feedback effort that you guys are giving me will really help as I continue to rebuild this course. And I know some people suggested too to like add videos. I guess like the math people have that. So that's all a good work in progress. And then I am a little behind on the My Open math stuff this week. Those of you in class were hearing my my AI woes, and they were being I was having issues coding as fast as I would have liked. But anyways, I appreciate all the feedback. It is super useful to get this launched. All right, we have a little bit of chapter 1, and then we'll start diving into chapter 2, unless there are questions. Oh, I will say deadlines, like I said, I'm not too picky about the deadlines. I think some deadlines, well, there's a couple of different reasons deadlines got screwy. I think on the syllabus I was just thinking the wrong date, but like I said, plus or minus a few days doesn't matter. Really, I don't care if you turn in all the work at the end of the year. I mean, that would be terrible for me just because I wouldn't finish, but deadline wise, you know, if you got things going on, better late than never. But yeah, just make sure you get in one copy because people have been sick too. So if you're sick, like that's fine if you need to switch modalities. But I just need one copy of the homework. Again, if you're in person, maybe you're doing paper, but some of you like my open math, so I really don't care. So paper, my open math, or do the online version. And even if you're in person, right, you could submit your homework through Blackboard if that's more comfortable for you. If you like taking pictures, you like keeping it. I really am not picky. Same thing with the quiz. I haven't opened up the quiz yet for like the in-person people just because I didn't quite want to go that crazy. But if someone wanted to, I mean, I'd be open. Otherwise, I'd rather we stick to either the My Open Math or online if you're online. And then, of course, in person for in person. And then, yeah. So homework quiz and then labs, of course, have to be done through Blackboard right now. I haven't gotten creative enough with the My Open Math, but next step in the future. All right, let's finish up a bit of chapter 1, unless there are like questions. Like I'm happy to do questions if we need to go back on conversions or if people are feeling okay. And again, I can always meet individually with people as well. Yeah. Oh, the videos, it would be the exact same thing. But I assume if you're in person, you like want to be in person is kind of the idea. Correct. Yeah. Yeah, but unless like some people have been ill, so like if you had to miss a week and you're in person, you would have the option of either making it up or you could watch the videos because all the videos should be here, but otherwise, again, you're in person. All right, so let's finish up temperature scales. And we had kind of teased a few of these points. Well, we're probably familiar with Fahrenheit. I forget. I think they just kind of set it to a standard of a cold day or something. And so this is, of course, 32 degrees Fahrenheit is where water freezes, so we're familiar with that. And then, of course, water boils at 212 for our Fahrenheit degrees. And what people find odd about the two different scales is, of course, if you look at the difference, right, between their freezing and boiling temperature, what do you notice about them? Right, zoom in. So are they the same? So no, right? So this makes the conversion between the two units kind of, I mean, I think it's not very intuitive. I think I've expressed that I know what a hot day is in Fahrenheit and I know how to boil solvents in Celsius, but can't do the other way. And so oftentimes we just look at our formula, and I do try to provide these on the exam for this case. But again, it is open notes, so write your formulas down. You have your periodic table. I would kind of have your cheat sheet. So you have your formulas. And then, so let's look at the difference between kind of Celsius and Kelvin. So Celsius and Kelvin are nice in the sense that they both go up by 100 degrees. So it's a little easier to understand the scale. And so, right, like a 5-degree temperature difference in Celsius is 5 degrees in Kelvin. And then they're kind of set to standard freezing and boiling points. So we have 0 degrees Celsius for freezing, 100 for boiling. And then, do we remember, we kind of mentioned it, I think, the first week. What was absolute zero? Excellent. So point where particles stop moving, or I'll just also say absence of molecular motion. It's pretty crazy actually how they do this now. You could always look up the research, but I want to say now they're down to like zero point 0.4 Kelvin if I remember correctly. But of course, like they thermally isolate everything, but you can only get so far. And now they're shooting like lasers at the same like rotational frequency as the molecules to like freeze them. So it's pretty crazy, the research they're doing. And then, okay, so that's defined as our absolute 0 point is 0 Kelvin, and then we scale from there. And so we have our temperature difference of 273. And sometimes you see this, this might have been in the homework of 273.15 if it references like exact. But for the most part, I wouldn't worry about this 0.15 on the exam. I'm not going to be a stickler over this exact or not exact. So that has to do with like sig figs. But usually I just use the plus 273, right, to go from Celsius to Kelvin, or subtract to go vice versa. So again, formulas, write them down. I'll try to provide them, but. And then just again a quick, I think you did this in lab, but just so we have this for our notes. And so what's density good for? Let's kind of back up for a second. Or what kind of property is density? Or what's useful? Or what kind of property is this? So yeah, getting there. So physical property, but then, right, this is kind of, I guess I was getting at intrinsic property. So it is a physical property, right? So that's telling you how dense. I should have put my notes somewhere else. And so intrinsic just means that it does not depend on amount. And so what I was also kind of getting at with density is a way to identify an object or a substance. So kind of the float test, right? Eventually, probably maybe this week even, I have a few samples of chemicals that are my personal chemicals, so we can look at some mercury. And of course, mercury is super dense, but right, it doesn't matter how much mercury there is, it's always dense. So that's what we mean, right? A way to identify a substance. You can take densities of different objects, much like how you did last week, right? And then figure out again the density and what metal it likely is, or at least close to, right? And so again, density is just defined as our ratio of mass to volume, generally given in grams per milliliter. Again, you saw that in lab. Could be grams per liter for gases. You can probably see different units. Again, out in the wild, it's just a ratio of the two. And so we'll do a quick example here. So 73.2 milliliters of a liquid has a mass of 61.5 grams. What is the density? And again, use your units to help remind you what the formula is, right? If you blank out, oh, I forgot how to calculate density, where your units, grams over milliliters, right? So again, that's giving you your mass per volume ratio. All right, I'll give you a minute or two to kind of try it, remind yourselves. So again, just plugging in our values here. So grams per milliliter, so 61.5 grams divided by 73.2. And then just thinking about sig figs. So at least, make sure you grab a copy of the lab. Also, I apologize for stapling on the wrong side. I don't know what button I hit. Did not work. But we'll be continuing sig figs in lab. And then just looking at this, okay, 3 sig figs, 3 sig figs. So our answer should be to 3 sig figs. So let's plug that in. And then we should have a density. So again, rounding to 3 sig figs gives us 0.840 there. And make sure you leave that 0 right for the correct number of sig figs. So grams per milliliter. Questions on that? Again, ask questions, right? Or else I have no idea if you're confused, and I'll just keep speeding along with the class. All right, one more example here. And so this is a good one. It's asking for volume. So of course you can do the algebra, but if you've never seen the triangle trick, now's a good time for it. So density equals mass over volume. And so if we wanted to find, it's asking for volume here. Oh, where's my, I was trying to get a block. There we go. So cover volume, and then it tells us, right, the mathematical operation. So we should do mass divided by density. Again, notice how those units cancel. So grams goes on bottom, grams, grams. Centimeter cubed on top, right, which is a volume unit. So length times width times height. So just remember that, length, width, height. So excellent. Oh, and I should have also said that 1 centimeter cubed is 1 milliliter. So that's a common, right, quick conversion that just happens. So yeah, just be aware of that. All right, I'll let you, so finish plugging that in, and then You can tell me A, B, C, D, E. And don't doesn't look like anybody's in the chat, but if you are, just please say hi. I don't expect people to, but all right, what do we get? Just go ahead and yell it. D, excellent. Anybody need that punched? I think we should. I'll do it just in case. So right, just punch it out. Again, excellent. Make sure you have whatever calculator you're using, although this shouldn't be too bad. And then this is just a quick definition if you see it. I mean, honestly, I never really do see this, but it could come up. And so the specific gravity, well, first of all, it has kind of two definitions. So like in general, like the general broader definition is just a ratio of two densities. But usually, but I mean, this is why I always think it's kind of silly, usually compared to water. And then what's the density of water though? Yeah, nobody knows the density of water. It's like your standard, right? Hint, hint. Yeah, so it's just 1 gram per milliliter. So then it really just ends up canceling out your units, right? So it's that's why I said it feels kind of silly, but that's what it is. And then we could do, I don't remember hexanes. Let me look up its density. Oh, I meant to put density. Asking Google real quick. So yeah, I thought it was that low. So just a quick example. Again, this is kind of almost feels a little silly. So hexane has a density of 0.659 grams per milliliter. So then we can say that, right, it has a specific gravity of 0.659. And again, right, no unit anymore. So just a ratio. But as I kind of mentioned, it really doesn't come up too much in practice. All right, any last kind of thoughts on the math portion, or at least what we've done so far? All right, so let's start chapter 2 then. So chapter 2, oh, and okay, I should have said, I need to go back and kind of fix your syllabus. So I mentioned that this was kind of a transition year, right? We just selected a new textbook. So all these like chapters that I have, they correspond with another textbook. So I admit, right, tad behind in the course just because there's a lot to do. But we're covering a bit of chapter 2. So we'll start with chapter 2. Not necessarily as in depth as this textbook, right? We just kind of want to hit the highlights. We don't need to worry about this constant composition so much, other than to say that define chemical formula. But then we will kind of skip around because we do want to get into electron configurations and how to do that. So like I said, I'll try to fix the syllabus as I'm working through like this whole course redesign. And again, I super appreciate the help with it because this will just make it better because as you guys have noticed, like I teach this class a lot. So just trying to make it better and more streamlined. All right, so we want to start familiarizing ourselves with the periodic table. So if you don't have a copy, get one. I should still have some extras. So yeah, I have a few. If people want to grab some, so yeah, whatever color. Yeah. I can make some more too that are not. Now you just have pink. Hopefully that's not offensive for anybody. I can make more of other fun colors. I think we're running out of the ivory. But yeah, so we just want to start familiarizing ourselves, right? Just kind of looking at the periodic table. I'm certainly not one of those uh, teachers, professors to make you memorize the periodic table, right? That's what the periodic table is for referencing, for learning. Like I said, right, the first thing you're going to want to do if you are really clueless about a substance, you're trying to figure out, is it an element, is it a compound, is it a mixture, right? First thing, does it even exist on the periodic table? So that's what you're looking at. And then we also want to define, well, what makes up an element? How do we get to these elements? And so looking at them as well. So right, we also have our synthetic elements. So these might have different names. Let's see, I was trying to compare it to the back periodic table because I think this one is now older. And so notice how it has like a lot of these unnamed. So I think now people have like claimed naming rights to more of them. So let's pull up our periodic table. So again, ptable.com is a really good website. And then we're just starting, again, like I said, to familiarize ourselves. So element is again just defined as a pure substance that can't be broken down. And then we'll get into this as we go into the parts of the atom, but we'll say that they're defined by the number of protons. And so the protons, like I said, we'll get into, but those are in the nucleus. But the big picture idea is, okay, well, if you change the number of protons, you change the identity of the element. And then, right, they just kind of start in order. And so this is where I like these different periodic tables. So starting with hydrogen, it's a gas. So, right, we have lots of gases. I do like that P table, again, you can kind of highlight it. Okay, well, there's not too many elements that are a gas either. And then hydrogen, notice, is kind of off in the corner. So hydrogen's just a little odd on the periodic table. And we'll see why that is as we also go through kind of the electronic structure. And so, right, we're kind of, it's always hard to get a starting place, right? Because you're just trying to kind of get your footing. Let's look at what elements are kind of relevant. So, of course, we're carbon-based life forms. So carbon is up over here. All sorts of different ways to color code. So this one is pretty heavily color coded. And then we can see that's a nonmetal. And then, of course, you're going to have a lot of hydrogen as well. So hydrogen, like we mentioned, up there. And then oxygen, again, that also makes sense. Organic-based beings. And then you're also going to have, right, nitrogen, and then various different metals. So here's a better list. So nitrogen, again, right, that's in a lot of like amino acids. So that makes sense that you're going to have a lot of nitrogen. And then, of course, you need ions, right, to make all those functions happen, all your transport chains happen. The ion transports, right, so calcium, phosphorus, potassium, sulfur, all these ions, right, many of them. So we'll learn, these are probably like cations also in solution, and we'll learn about which is which. Again, just kind of looking at what's relevant. And then again, we just want to compare it. So we'll go back to the periodic table, but just comparing it to a compound. So what's our definition of a compound then? Or at least one we can kind of work with. What do we say?
Consistent formula of more than two elements.
Excellent. So consistent formula of two or more elements. I'll just kind of put different in parentheses. So we're thinking back to the allotropes. We're thinking back to things like the buckyball. Okay, that's still considered an element though, because that was only one type. But now if we have a different type, so you guys recognize what this one is? Yeah. Yeah, and that is water. I almost can't tell if we're making jokes over here. And then now I think of the H2O2 joke, right? Everybody knows that one where someone's like, I need a glass of H2O2, and then someone else is like, I'll have H2O2, and then of course H2O2 is hydrogen peroxide. But anyways, bad chemistry jokes to start off with. And this is just showing you different ways that they can be represented. So we have this kind of more space-filling ball model, and then each color kind of represents different elements. So we have red, for example, is oxygen, and then blue tends to be nitrogen, black is carbon, white is hydrogen, and then you'll have like yellow, which is usually sulfur, or any of those other kind of group 6, which we'll get into. So selenium. You'll have purple for phosphorus, or again, sometimes other group 5. And again, we'll get into like, what are all these groups that she's now rambling at, right? So we have to start somewhere. And again, that's can make chemistry difficult initially, right? That like, we're throwing out these terms, we got symbols, now we're throwing out these stick models. So again, just hang with it, ask questions. We're trying to just get everybody on the same page as to what the heck all these symbols mean. Green. So green tends to be any of those halogens. All right, those are the kind of main colors. There's like silver too, but those tend to be like expanded octet special stuff. All right, so again, these models like try to show also like geometry, how they're shaped. So things to start taking in, again, right, we're starting somewhere and then we're building. But we can see, okay, well, water takes this bent shape, and we'll revisit water and why it's bent. So over here, so this little molecule shown. So now we have kind of more ball and stick, so less like space filling. So you can, again, see a little bit more definition. So this is carbon, carbon, and then we could also write this out. So we can write it out like this, of course, and draw out our hydrogens. So right, the difference. So this is showing, again, more 3D. You can appreciate how they're very far apart. So basically there's like space between them, but again, we're not going to go there, but that's maximize space. This doesn't really show that, right? So same molecule, but it's just kind of written 3D. That's a little deceptive because it's not flat. And then another way that you could write this, though, is just a line. And that is the same thing. So organic chemists use like this stick shorthand. So again, that would be ethane then. And so here's another example of that kind of shorthand organic chemists use. And then you want to just at least start getting familiar with what the heck this all means. So I'll redraw it now more explicitly. And so the thing with these organic structures is that they don't show you carbons or hydrogens explicitly, and they only show you hydrogens that are on like a nitrogen or if there was one on an oxygen. And so let's rewrite this molecule. So that means that this point is a carbon, so now I'll draw that. So nitrogen, this little group, so this is called a methyl group. And so that's a carbon, and then carbon, so we'll keep seeing this, but carbon needs 4 bonds. So we can't just have a carbon hanging out. So that means that this methyl group, and this is what a methyl group is a CH3 here. And you could also abbreviate it as a CH3. And I'll do that on this one to show. Sorry, I almost got lost in my ring. So again, another point, another carbon, nitrogen, another methyl group, so I'll abbreviate it slightly, right, as CH3. So that's pretty common. And then carbon here. Carbon at this point. Bond, double bond. Okay, just getting down. So nitrogen, double bond to another carbon at that point. Nitrogen. So you can see this is a 5-membered ring. And then just double checking that carbon, right, 1, 2, 3, 4, 1, 2, 3, 4. So if this was lacking a bond, and I'll show another example, but if we didn't have 4 connections, we would tack on a hydrogen, but we do. Oh, this is a good example. So look, 1, 2, 3. So this carbon's missing a bond. Hydrogen there. And then last bit, so right, another methyl group. So CH3. And then you would want to practice writing out the formula. And so usually it goes like carbon, hydrogen, nitrogen, oxygen, and then other elements in like alphabetical order. And then that being said, they could be grouped and regrouped kind of depending on like what functional group it is. But again, that's kind of going too far down. But now we can count. So let's count our carbons. I would have an easier time on this one. So 1, 2, 3, 4, 5, 6, 7, 8. Double check that. 1, 2, 3, 4, 5, 6, 7, 8. And did y'all get that? Okay. Also, so I know you guys probably like aren't thinking about OChem, but this is like seriously half of OChem is like count and then count again and make sure that you count. Like counting is so important in chemistry, so right, we don't need a bunch of high level math. Okay, hydrogens 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. And then again, there were no others, so I can pull up an example of like an alcohol group or something where the hydrogen is shown. Nitrogen 1, 2, 3, 4, and then 2 oxygens. And so that's our chemical formula. I'll show another. Yeah, question. Oh. So yeah, you want to write it below for chemical formula. So it's always a subscript. Up would be like if there was a charge on the molecule, like if you did sodium like 1 plus here, then that's telling you that, well, we'll get to it, is a cation. But yeah, Good. Yeah, ask away, because again, there's symbols, and I forget what you guys don't know, and I'll just start writing symbols left and right. And so then this molecule I just wanted to show. So this is benzene. And then writing out benzene more explicitly so we can see it's a six-membered ring. Oh, sorry, I tried to show both structures. And then this double bond can alternate, which is even more interesting. So make sure every carbon has 4 bonds. So I'm tacking on hydrogens to all those ends, and you can kind of see it, right? 1, 2, 3. So okay, it has to have a hydrogen. Our formula is C6H6. And I mean, this is probably like way too much for this class, but I think it's still good to at least mention that benzene is a flat structure. And so again, this changes the geometry and everything, so you can be thinking about that. All right, so let's go back to kind of atomic structure. And like I said, getting familiar with the periodic table. And so all atoms have the same subatomic particles. So we have protons, neutrons, and electrons. And we're not interested in like the other like subatomic particles at this point. So we're just focusing on these. And so protons and neutrons are found in the nucleus. So that's the center of the atom. And then electrons, and they are negatively charged, which we'll get into, but they are found in, I'll just call it our electron cloud. I mean, truly it's a probability density map, but that might be, like I said, a little bit too much for our introductory class. And then other key points that we have is that the protons and the neutrons have nearly identical masses. And so this means that they basically make up our atomic mass here. Well, they do. And so usually I have some formula of like protons plus neutrons equals our mass. And this would be of like one individual atom. So we'll kind of get to what I mean in a second as well. Don't want to jump the gun on things. And so the mass of a proton is 1.6 times 10 to the negative 27 kilograms. The neutron is about the same. And then the electron, if you look at the order of magnitude, so 10 to the negative 31, that's why it's considered negligible. So we don't even include it, right? And so usually we just say, okay, our proton has a mass of 1 atomic mass unit, and our neutron is 1 atomic mass unit. And so that's why we just add them up. At least, again, for an individual atom. And then this is a good summary chart. So the little point at the end was that our proton is considered to be positively charged, and then the electron is opposite of that and considered by convention to be negatively charged. And then again, equal in magnitude, so that's important, opposite in sign. Neutron has no charge. And then again, summary, what we care about. So again, our proton is 1 AMU, neutron is also 1 AMU. Relative charge, so proton is considered plus, and electron is -1. And then you have your Coulombic charge here, but again, I don't think we need this, especially in this class at this level. All right, so as I mentioned, right, we change the proton, we change our identity. And so we can go back to our periodic table. And again, grab yours or grab whatever one you're going to be looking at on the exam. Make sure you know how to read them. So, right, we have our atomic number in the upper corner, right? Atomic number. And so your atomic number corresponds to your number of protons. So there it is here. So again, atomic number equals our number of protons, which is again the identity. And so more pictorial representations. So we have our nucleus, and red is used to symbolize our protons. So we have 2 protons. And then right for this isotope, so we'll get into the definition of what that means. But for this isotope, we have 2 neutrons. Again, that's what's found in the center. And so we can say, right, we have helium, 4 for the mass, again, 2 protons. And then again, we just really want to make sure we're all on board and on the same page. So if we go to helium, okay, 2, right, upper number there. So that's its atomic number. And then down here, well, like I said, I don't want to jump the gun, but this is more of an average mass, but we do see that most of the helium is going to be this mass of 4 with obviously 2 protons. And I'll go ahead and write the atomic symbol, but we're again kind of getting there. So this is another way to write things out. We'll see this again. But again, I just want to start introducing things. We'll see them again. And so when we write our symbol like this, notice that our mass goes in the upper corner here. This should correspond to the number of protons or atomic number. And then, right, helium. So these two should match, right? So those, I'll just kind of say match from P table. Right, this is just like an identity. And then again, the mass of that particular isotope. And then to your question, if this was charged, we would add a charge here. But no charge for helium, and we'll kind of see why. Or at least generally speaking, helium shouldn't be charged. And so again, kind of looking at this example shown, if we could zoom in on an atom. So we have 1, 2, 3, 4, 5, 6 protons again. And then let's see, 1, 2, 3, 4, 5, 6 neutrons actually as well. And again, just reassure yourself, okay, carbon, yes, I see that number 6 there. So that matches with the atomic number. Again, number of protons is 6. And we'll get there. So again, we'll explain why this mass isn't quite 12. But this isotope, so that'd be 12 carbon. And we could write our symbol like so. So questions so far? Again, I'm just kind of going to keep going unless you guys flag me. And then as you're kind of seeing, okay, well, elements are arranged in the periodic table by their number. And then we're getting to kind of why the periodic table is the way it is. And, oops, sorry. And so it says here that elements within a column have very similar physical and chemical properties. So that means that we can, discuss their reactivity. So again, increasing atomic number. We'll kind of, again, discuss all this as we look at its structure. All right, let's look at isotopes. And so now we're kind of getting at, well, why doesn't this number match? Right? We just said that it should be a whole number. Well, why not? And well, that's because we have this existence of isotopes. And so these things just like exist in nature, by the way. So we won't get all philosophical right now on, again, whether we were created or whether it was a big bang or whatever. But anyway, so scientists don't really know why, but okay, we have a certain abundance of isotopes. And all that means is that we have elements with different number of neutrons. And so we'll look at this example, but let's go through another one that you might be more familiar with. So of course we mentioned carbon. And so carbon 12 is the most abundant. So it's about 99% roughly. And then have you guys heard of carbon 13? I don't expect y'all to have. So some people have, so that's good. I'm most familiar with it because chemists like to take what's called C13. Oops, sorry. Can't write. So C13 NMR, which is just basically to get a picture of a molecule, but again, we won't go down this rabbit hole over what NMR is unless you want to ask me later. But that's what this one is used for. Now with modern instrumentation, C13 NMR is actually not a big deal anymore. And I mean, you wouldn't appreciate it. You go sit at the computer and collect a beautiful spectrum in like 2 minutes. But why it used to be difficult is, of course, C13, well, 99, that's not much left. So 1% is C13 NMR. And so then obviously, if you have just a sample of something, right, like let's just say, okay, you have 100 grams of compound you wanted to look at. Well, only 1 gram of that is C13. When you take an NMR, you can't put 100 grams in there. You take like a tiny milligram sample, stick it in a tube. And so it used to take like 30 minutes to an hour to collect a good carbon 13 spectrum for just looking at your data. Because again, you're only looking at like 1% of this tiny population. But now modern NMRs are pretty powerful, and I mean, I don't know what they do to make them have better resolution. And then that leaves us the last common one is carbon 14. Anybody know what this one is used for? It's not fertilizer. Yeah, you said carbon dating, right? Yeah, so carbon dating or radioactive dating. So kind of two terms. And so the key point of carbon 14, I mean, other than it being like less than 1% abundance, I would have to look up the exact tiny percentage. So less than a fraction of a percent. But part of these isotopes, and again, this goes back into like, we don't really understand why completely, but when this like mass ratio gets off, and so let's also explain the difference between them. So sometimes when this like proton to neutron difference gets weird, and again, it's really hard to predict. Like I said, scientists don't really know what makes isotopes, why certain ones are radioactive. Like predicting them, I mean, we can obviously observe them, but prediction. But this is basically unstable. So for whatever reason, again, it's unstable. And so it has 6 protons, right? Because carbon always has 6. And then this is our mass number. And we said, well, protons plus neutrons equals our total mass. So how many neutrons does this one have? 8. Excellent. So 8 neutrons. And again, that's unstable for whatever reason. And it starts to decay. Anyways, we don't need to go there. But that is why it's used for radioactive dating. There's some assumptions that are made, but basically how it works is, okay, if you're a living organism, you're actively incorporating carbon, and then again, that certain percentage will be carbon-14, and then when you die and stop consuming carbon-14, then they can measure the ratio and figure out the decay. All right, so that's that, but that's all to say that these are these different isotopes. Oh, and then, well, how do we get to this mass here? Well, let's say we could individually weigh them. I mean, basically what you want to do is take your weighted average, but the way to kind of think about it is like, let's say you have 100 carbon atoms, right? By our standard here, we would expect about 99 of them to weigh 12 mass units. Again, if we could have them stand on a mini scale. And then one of those would weigh, of course, 13 AMUs for being our carbon-13. And again, how many neutrons then are in carbon-13? 7. Excellent. So you guys are on the ball here. Okay. And so if we were to take our average, so again, the formula ends up being that we take our atomic mass unit, so 12, times our abundance of 0.99. So again, that's the same thing as if we were to do our weighted average, plus 13 times, and it's 1%, so 0.01. And so we do get about what's on our periodic table. And of course, we would get more significant figures if I was using better values. I was just kind of quickly estimating to show you where they come from. So you'll have some more practice in your lab. But that's how we get this number on the periodic table, which is a weighted average. And so I'll just point out another one. For example, like bromine, it's about, the mass on here is shown as almost 80, right? But there's no isotope of bromine 80. It's 79 and it's 81 and it's 50-50 actually, which is, that's why I like bromine, but bromine's kind of fun for that. So bromine, so again, it's 50% bromine 79 and 50% roughly bromine 81. So it gives us, right, a rough average of about 80, which is again what's reflected on the periodic table. So again, there's no isotope of 80 for bromine. All right, we'll take a break in a second. So just kind of looking at this end here. So like we covered, one way to write it, mass number on top here, atomic number on the bottom. Again, right, that's from your periodic table. And then your chemical symbol that should match your atomic number. So I kind of highlight them, right? They should match. And then there are, of course, other representations. So you might see this sort of thing. Again, chemists kind of shorthand like this, especially when talking about NMR. So like there's 31 phosphorus, 19 fluorine, NMR. And so chemists might just write it like so as well. All right, let's do this last example and then we'll take our 10-minute break. I know you guys have been going. So let's see if we can find this. So what's our atomic number, mass number, and symbol then of a chlorine isotope with 18 neutrons? So give you guys just a minute to look at that, right? You have your periodic table, hopefully. All right, so tell me what we get. So what's my atomic number again? Where do we get that? So 17. And again, just so everyone's on the same page, right? Go to your periodic table, chlorine, perfect. And again, right, start getting yourself familiar with these symbols. And capitalization does matter. I should have mentioned that. But, right, we can just take a moment to appreciate we have some that are a single letter, and those are going to be capital. And then we have some that are letters, like chlorine. So that's a capital C, lowercase l there for chlorine. Good. 17. And then what did we find was our total mass then? So 35. So now I'm rewriting our symbol like so. All right, yeah, let's take a break there before I'll keep getting excited. So we'll take a 10-minute break, so maybe come back around 2:06 or so. 2:06, 2:07. Yeah, Okay, do we all make it back already? Also, I apologize for it being hot in here. I tried to mention something to our wonderful secretary, so we'll see. Uh, yeah, unfortunately, it's controlled by the other university, so we may have to, like, maybe a while, but yeah. If it's going to be warm, we'll try to get that fixed, so I apologize. Alright, so let's cover one more thing before I forget. So we can also have what are called ions. And so broadly speaking, these are defined as charged, well, atoms, but I mean, could get into polyatomics or any other species. So basically a charged substance. And so typically we'll look at, for example, we could have a cation. And so a cation is defined as a positively charged atom. And so one example, and this starts to tease reactivity just a hair, but basically we'll learn that our metals tend to give up electrons. And so that's what makes a cation, right? So you lose an electron. And so some other formula that I like when looking at ions, at least how I think about it, is we have that our charge is equal to our number of protons. And I always think in my brain plus electrons, but you're also thinking that like, okay, well, electrons are negative, right? So if you have the same number of protons plus electrons, well, that's going to cancel out. And then if we have our cation then, so then we should have, right, more protons than electrons. And so some example that we'll typically see is, well, if you have lithium metal, and at some point we'll do this in person in lab or as a demo, but lithium tends to give up an electron and it'll become lithium plus, and we'll see why it just gives up one electron. We're slowly getting there. We can also have an anion, which is then a negatively charged species. So species again. Right now we're focusing on atoms, but like I said, we'll move on to polyatomics later. And what the heck that is. Uh, at the very end, organic acids and bases start to get into these negatively charged species. But anyways, they are usually from accepting electrons. Yeah. Oh, so like I said, species being like an atom, or like I said, we'll get into polyatomics, like citrate, right? Like citric acid, citrate. Citrate's a negatively charged species. Like all your salts now, or like I don't know what supplements people take, like lithium orate, for example. Orate is just your counter ion. So that's I believe it's just one negative charge. And so anyway, so we'll learn what tends to accept electrons. So generally this is going to be our nonmetals. So now we're slowly starting to like get into things. So nonmetals tend to accept electrons. So this could be like fluorine, for example, accepts 1. Oxygen you'll often find, right, -2. We'll put in like chloride, salts, bromides. So any substances could also be found as salts generally. Sodium, right? You don't take sodium metal, you take sodium chloride. Or sometimes, right, you have sodium iodide, right, for the iodine, the iodized salt. Actually, I think they use potassium iodide if I remember correctly. So some mixture, right? You could have a mixture of salts. So then iodide would be your anion. All right, so first we're just kind of looking at our periodic table. So we're starting to get familiar with our families. So we have, and I might, like I said, I might get overexcited and start getting into our electronic properties just a little bit. So we have our first group over here, and then we do have this little one, and these ones, they can correspond with our valence electrons. So one valence electron, so for hydrogen, and that would be right your kind of neutral hydrogen here, so one electron, one proton. And then helium, and there's like a huge gap here. Well, maybe I won't get too excited there as to why. We'll save the why for like a little bit later. So then helium, we'll save this. So helium's part of our noble gases. And maybe we'll start here. So noble gases tend to be unreactive. And let's pull up our P table. And obviously, right, they are gases. And then we will see this in person in lab. But you can, of course, pass an electrical current through these gases that excites the two little electrons that it has, promotes them to higher energy levels, and they relax back down and give off pretty colors. So helium is like an orangey-ish color. Obviously, it's just a colorless gas otherwise. Same thing with neon. So unfortunately, true neon lights are hard to find nowadays. Everything's just LED. Obviously, there's a huge cost associated, right, with a gas. So you have to have a gas in a tube and electrify it. And then it does leak over time eventually. So neon's a nice orange gas. And, right, I just said that they're inert. So we'll keep looking at our gases, but just a couple of highlights of noble gases. I feel like I misspelled gases. So generally unreactive. That being said, you know, I always make a point, chemists are always trying to do something new, right? So you can make compounds with especially like these heavier ones. So xenon, krypton, so you can kind of force them into to make molecules. Otherwise, they're fairly inert. So argon is sometimes used in research as like an inert gas. So argon is a pretty inert gas. Obviously, I mean, we just said that it's a noble gas. The problem with argon and why researchers don't just use it willy-nilly is argon's expensive. But typically, so now I've gotten too excited. So typically, nitrogen is used and considered fairly inert to create like a dry box, it's called, or these like inert atmosphere box. But sometimes nitrogen can react with something. And so some things react with nitrogen, or some people are interested in nitrogen chemistry. So then obviously if you're trying to react with nitrogen, you can't use a nitrogen box, so you have to use argon. And then one of the few compounds that does react with nitrogen is lithium. And it's kind of hard to tell from this picture. It should be like more of a bluish sheen. I don't know why that looks more like red to me. But kind of this bluish looking compound. So again, if you didn't want that, argon is used, but argon is expensive. And then krypton, xenon, and then of course radon. Oops, I don't know what I clicked. So then radon is going to be radioactive. And so sometimes, like, I don't know if you guys are familiar with old homes and you have to do like radon testing sometimes and like make sure that your basement isn't off-gassing a bunch of radioactive gas or anything. Now what did I click? Oh, get out of these properties. Oh, I don't know how I click specific heat. I didn't mean to do that. All right, so like, oh, and then the other thing, so looking at these numbers, so we'll kind of skip them. So we have 1, 2, and then I would follow these other numbers. So 3, 4, 5, 6, 7, 8. And so noble gases, why they're unreactive. So they're generally considered to have what's called a full octet or 8 valence electrons. But again, we'll revisit what this concept means in more detail, right? We're just kind of hitting the overview, and then we'll come back again. So then starting to look at the rest of the periodic table, and again, y'all might be familiar with some of these things. So let's look at our alkali metals. So group 1 over here. So hydrogen, you can kind of tell by the coloring, right? It's not considered part of it. So it's more of our, it's classified by this periodic table as our reactive nonmetal. Sometimes you see hydrogen just kind of like by itself as like hydrogen, since it's special, right? It's like a flammable gas. And then it does have 1 valence electron, just like all these though. And again, we'll revisit kind of what that means. But then all these alkali metals are shiny, and then they're pretty soft, like you can cut them. And so alkali metals are in red on this periodic table. And then so other properties, so soft, shiny, and then obviously they're known for being water reactive. Or maybe not obviously, but that's what most people know them for. So all these are water reactive. So I'll do lithium, sodium, potassium for you guys in person, but potassium is the limit to which you can work with stuff in air, and it does auto-ignite in air. So there's sodium, and again, that's a freshly cut piece of sodium, so as soon as sodium is exposed to the oxygen and water just in our atmosphere, it starts to oxidize and make sodium oxide. And again, once we do this in lab, we will see it. And then potassium, I think I mentioned in lab in passing that I have sliced potassium in air before and then had it auto-ignite in air before. Again, I knew that was a possibility, and potassium is your limit. You can still cut it without it auto-igniting, but sometimes it does, catch on fire. But then rubidium you cannot work with in air. It is too reactive. And so you can kind of see that in this Wikipedia picture that it's in the sealed ampule now. And if you were bored, you could look up YouTube videos, right? People are always busting ampules of rubidium. And again, right, as soon as you bust it open, it starts exploding. So same thing, cesium is, again, similar. So same thing, sealed ampule, right? Beautiful metal there, and then they get nice and soft. Francium is radioactive. So hopefully you won't see anybody busting open some francium. See, they don't even have a picture of it. So all right, so that's our alkali metals. So I'll put 1 valence electron. And so this 1 valence electron, it's hinting at us again to what we'll find, right? So that's why we'll find lithium plus, sodium plus, potassium plus, rubidium plus. So anything in that group, right? So they can only typically lose 1 valence electron. And we'll come back, like I said, we'll come back to it. We'll keep kind of like reiterating the same concept in a few different ways so you really feel like you understand it. All right, so let's move over to our alkaline earth. And again, just kind of start looking at those. So two valence electrons now. And pretty similar. They're just a little bit harder, right? Still metallic-y, still metals. That's another like general property. So you kind of see these periodic trends. And so on this side of the periodic table is considered to be the most metal character, and then like decreasing metal character as you go across. So obviously that makes sense too, because we end in our gases and our nonmetals. And then we have our metalloids, but again, we're kind of working our way over there, just trying to give big picture overview as well. So going back, again, just make sure you understand and can make the correlation. So, okay, we have a 2 here, so that's telling us, well, all these have 2 valence electrons. So this would have, right, 4 total, though, for the neutral. So we'll see that. So they are still can be water reactive, but less violently so. So alkaline earth. So I'll just say kind of like mildly water reactive. Sometimes I like to say that they kind of need a little extra kick. So they definitely react with acids though. Let me just say acids. React with acids. So HCl or nitric would be acids. They would dissolve in them or react with them. So we'll do that in lab. You'll react, like a very typical reaction is to do magnesium and hydrochloric acid. And well, we can start to write out these reactions. So magnesium plus HCl, and we would need 2 equivalents. And well, now this is kind of going a little bit too much, but we can see where we're going. So magnesium has 2 electrons to give up. Chloride, well, each one of them wants -1, so we make this magnesium chloride. Again, balancing out our charges, but we'll revisit all this, right? I'm just trying to like say this is where we're going. This is what all these things mean, but we're gonna be back. Like I don't want to lose people. And the first few weeks of chem are always kind of the hardest, I think, because again, you're learning a language essentially. And then we'll make gas, and other things can be said about this, which again, we'll revisit. But this is a typical reaction structure where you're evolving a gas. We're making, right, our salt here. Charges are balanced, so that's what we're going to see. And again, we'll see that magnesium is nice and shiny in person. There's another example, but you will see this. So calcium, same thing. Calcium reacts with water pretty nicely. So again, we'll see that. We have fresh samples too. I think I have some old ones that have oxidized, and you can compare. And I had some fresh ones ordered a few years ago, which are holding up nicely. So again, right, silver, metally, yay. Strontium. Strontium again, mildly water reactive. I had to quench some strontium before. Barium, yay. Just kind of again appreciating. And then again, radium becomes radioactive. And so past like 86 and beyond, you tend to have a lot of like radioactive elements. So again, that's has to do with the mass ratios, the protons to neutrons, and for some reason, again, those just start to get out of balance. I mean, I'm not, again, it's we don't really know why they do this, but we again see that those heavier elements or short-lived and radioactive and start breaking up. All right, so then we'll keep going. So we're admittedly basically going to skip the middle periodic table. So this is our transition metals. That's my favorite part of the periodic table, but like I said, just a little beyond our course. Uh, we'll still like name them. We'll talk about them a little. Transition metals. So why they're fun is they can create issues because they have different oxidation states. Which try to simplify, right? You could have like cobalt 2 plus, cobalt 3 plus. Same thing, right? Iron 2 plus, 3 plus. Oh, and that is what this periodic table is good for. I forgot about all this information. And so this periodic table has like all the common oxidation states. So I think the most common one is on the bottom. So like iron 2, but then there's 3, there could be 6. And then this is not like all inclusive. It just kind of gives the main ones. Uh, Chlorine gets crazy, but you mainly want to focus on -1 for those. So I'm mainly looking at the transition metal part for this. Palladium, right, 2 and 4. You can also have 1. Manganese, 2, 4, 7. So those are typical ones. So again, that's why they're crazy. We'll come back. We'll get to naming them, but we're really not going to dive into them. And we can briefly kind of say d orbitals, but again, now I kind of feel like I've said too much. I'll just get overexcited, but so we'll kind of skip those. So then let's look at our group 13 over here. Again, just taking our tour of the periodic table. And so group 13, again, I would write on your periodic table that you know that this means we have 3 valence electrons at this point. So we'll see how we treat that. So 3 valence electrons. And then we start to get into this metalloid character, right? The stair step or semi-metals as it's labeled on here. You could find maybe small discrepancies with this stair step. Hopefully not, but again, I try not to quiz you over like trivia like that all the time. I mean, we still want to do some non-metal metal, but boron. So let's look at boron. So again, it's still pretty metally in character. And then boron also has like a lot of research going on, high area of research. So that's pretty cool as well. And then aluminum. So you guys are probably familiar with aluminum, right? Although, yeah, so we have aluminum, obviously aluminum foil. Gallium is a fun one. I don't know about, well, so gallium, yeah, they'll probably, well, if you heated them up, are you sure you're not thinking of like mercury? Because, yeah, mercury is the one that like usually what people think of. So gallium, it maybe could do that. So gallium, people know, I don't know if anyone's ever read the book The Disappearing Spoon. It has like fun chemical tales. But gallium melts at like room temperature, so it's like melts in your hand element. So maybe if you melted gallium and put it with like aluminum, because the whole thing is then they'll start to form like a mixture or an amalgam, right? But kind of mercury is more famous for doing that, right? And like now there's YouTube videos of I think people putting mercury on their aluminum max. Just because, right, again, mercury will dissolve that aluminum, just make an amalgam, which makes it weak. And then, I mean, you can make any sort of like metal amalgams, but yeah, I'm not familiar with like gallium and aluminum explicitly, but we could always ask like the internet. Like I said, if you heated it, I think that could be an issue. Because gallium, I mean, at least when I was trying to work with it one time, I didn't find it as melty as like it should have been, and I was like staring at it, like trying to smash it up. So that was gallium, and then let's just keep going down. So indium, I don't have any experience with indium personally. And then thallium. So thallium is dangerous. So now we start to get to our kind of nasty chemicals. So thallium metal is fine. It's the salts that are bad. So the salts can be kind of super toxic. So I did have to work, or I tried a thallium reaction once in my life, and then thank goodness it didn't work because I did not want to work with thallium on a regular basis. So yeah, it's toxic. I feel like it also creates, yeah, I wanted to find that. So can cause hair loss. So be careful with thallium compounds, but yeah, they're toxic. So historically used as rat poisons, but again, like you don't want thallium in your environment. All right, so then that leads us to group 4 over here. So 4 valence electrons. Something that maybe we should point out, I don't know if this is too early or not, because we'll kind of see it and not see it. So we can start to get into oxidation states a little. And so it goes back to like this first one valence electron. So if it's going to be in any oxidation state, it's 1 plus. Our second group is 2 plus. That means, right, group 3 was 3 plus. But this is where things can get funny, and I call it that there's like a switch, because, well, this is, again, kind of getting to where we're going. But we'll learn that our noble gases are stable electron configurations. We'll figure out like what that means, because again, I feel like I keep throwing out terms at you guys. I'm not trying to leave you guys behind. But we could get to helium if we went 1, 2, 3, 4. So minus 4, 6 minus 4 would give us 2. So we'd be at helium's electron configuration. So we could lose 4 valence electrons is what we're saying. Or if we went the other way, 1, 2, 3, 4, that would get us 6 plus 4, 10 to neon. And so this is where there's kind of a switch. So you could find both plus 4 and negative 4 oxidation states for this group kind of formally. But that being said, what we'll find is, again, most of our kind of ionic compounds are from this side of the periodic table, from our metals. And again, we have our stair-step barrier too, kind of helping us of our, again, metals versus non-metals. And again, non-metals tend to be negative oxidation states. And then carbon formally can be all over the place, but again, that's kind of maybe beyond this class just a little bit. And then nitrogen, oh, sorry, I got ahead of myself. So let's go back to group 4. So carbon is, of course, a nonmetal. So black powder typically, or like we've discussed the other forms of carbon. Maybe some of you guys have prettier forms of carbon. Silicon is also fun, so right, kind of a metal. So this goes back to our metalloids. You may be familiar with like silicon being used as semiconductors as well. What other fun things about silicon? Germanium. So silicon, germanium are all, again, kind of similar. And there is research interest since they're analogous to carbon. Yeah. Oh, valence electrons. I'll write it out. So yeah, VE equals valence electrons. And that just means our outer electrons. All right, so going back, oh, like I'd mentioned, so carbon, there's a hot area of research for carbines, or at least, I mean, it was hot maybe in the 90s or 80s. And then after that, silicon and germanium took over. And so that's what I did some research on. And then if we keep going down the periodic table, so now we're back to metals. But the problem with tin and lead is they can be, of course, toxic again. So tin compounds are known to be toxic. So again, like salts, you wouldn't necessarily want to work with them. They could cause right convulsions and stuff. Lead as well. And then, oh, that also goes back to another issue with tin. And so what do you guys know about your soda cans? So your soda cans, right, they're made out of like tin or aluminum typically, but what do you know the secret behind your aluminum cans? Yep, yep, yeah. So you guys know the secret, and so yeah, that's the issue. So I don't know if they still use like tin cans anymore, but any sort of acid, so we mentioned, right, acid can react with metals, and so that can happen over time, you know, with both aluminum and tin, again, depending what your can is made out of. So yeah, they put some sort of plastic liner in there to prevent that. So, so much for plastic free. Anyways, we won't get into microplastics. And then lead, of course, again, lead, that gets into a heavy metal, which then gets into, well, what's the definition of a heavy metal? So there's no like set definition of a heavy metal. It's just kind of considered something that is difficult for your body to expel, and then they tend to be obviously heavier isotopes on the periodic table, but and then so kind of continuing, just again our general overview. So at some point I'll bring some nitrogen in as well. I need to figure out when would be a good day to bring nitrogen, but either we see it in the 5+ oxidation state, so right 5, or usually 3-. And so that's nitrogen, phosphorus, so let's look at those. And then now we're in the nonmetals, right? We're pretty solidly a nonmetal. And so if y'all remember, so most of the air that we breathe is nitrogen. And then, like I said, at some point I will bring in liquid nitrogen for y'all that has been obviously cooled. And then we can see it, or I don't know. I don't know what fun trick I'm going to do yet, but we'll just appreciate some nitrogen. Safety, though, so thinking about safety before, if we're talking about bringing in nitrogen, so of course you have to be aware of like the gas displacement issue. So for example, you wouldn't want to be in like a small space with a liquid nitrogen tank. Like what if it started off gassing, or you spilled the whole thing and right the room filled up with nitrogen, then you wouldn't have any air to breathe. So anyway, safety tips. Many ways to technically die with chemistry. And then we went into white phosphorus and all sorts of allotropes of phosphorus. So again, officially banned, but still used in war. And then phosphorus compounds are all sorts of useful as well in research, although phosphines can kind of be toxic. And then arsenic, so that is toxic. And then again, we go back to the metalloid character, right? So we can see, again, just kind of appreciating that. Okay, phosphorus looks powdery. Arsenic is back to metalloid. And then going down, antimony. Never really worked with antimony. Bismuth is, of course, fun. Oops. Bismuth, you always see them like selling it at the Like, I don't know if anybody made it to the rock convention, but they had a bunch of bismuth for sale. It looks really cool, kind of like rainbowy. Why do I keep clicking on stuff? Sorry. And then, so our last two that we'll kind of look at before we do our second tour, second trip. So we have our chalcogens, or group 6, or the smelly group. And so, of course, oxygen is not smelly. So oxygen, obviously, we breathe. I don't know. See, I would make promises, but I'm not sure that I would keep them. But we do have a tank of oxygen. And like I said, if I had liquid nitrogen, I could do this. So depending how interested people are, like, this is an option. But what's fun is, like, yes, if you condense oxygen down, it is blue, which is fun. Just be careful with this. So, of course, oh, that being said, did you guys watch the Artemis 2 and stuff? Yeah. So that is what they use as their rocket fuel. I was researching it, but they use liquid oxygen and liquid hydrogen, and like, I don't know. To me, that's just like effing awesome. But I'm probably just like overexcited about stuff combusting. But that's most chemists are like either pyros or druggies or both. No, I'm joking. But something else that we can kind of do is like explode balloons. So those are other like fun demos. So you can react like a hydrogen balloon, which I was thinking about doing this week, and then you do an oxygen balloon, and then you do the mixture, and it's a much bigger like boom because you're forming like water more instantly. But that being said, so liquid oxygen, obviously it's a fuel, it's an oxidizer. And so once you get it in this like liquid form, it can also be pretty dangerous. So if it's mixed with like an organic, it can also cause a fire. So that was like a hazard in my uh, research work, because what students can do, or PhD students, I mean, is if you make a mistake and you start, let's say I always joke that like half of grad school is dissolving something and then pumping off the solvent. And so in this process, it's pretty easy to accidentally like leave a line open to the atmosphere. And then if you start sucking in the atmosphere, you could potentially condense liquid oxygen in your trap. And if you do that, you have to like evacuate the lab, which I never have done that personally, but my fellow grad student one time did that, and we had to just leave the lab. So yeah, you don't want to condense liquid oxygen because, like I said, if there's any organic around, it could potentially be explosive. So it's a pretty scary danger. Like, people take it seriously. It's just fume hoods shut, leave, and then you just give it time, and ideally the pump will pump away the oxygen first and not the organic solvent. But anyways, so that's oxygen. And then we move down. So then sulfur starts our smellies. Sulfur itself is not smelly. It's the hydrogen sulfide that starts to smell. And then, of course, right, sulfur decomposes obviously over time, reacting. So it starts to get smelly. And then obviously other sulfur compounds tend to have that like egg smell. There's mercaptan's the famous, maybe not famous, but they put, that's what they put in natural gas. So natural gas itself is odorless, excuse me, but right, it smells the mercaptan or methanethiol. Smells horrible, obviously, so they put a little bit in there so that you know if there's a natural gas leak. But so then those are the smellies, and then it just gets worse. Although now I don't know if like these stories are exaggerated, but selenium compounds are supposed to be pretty smelly. And then same thing, I think, with tellurium. Do any of you guys like watch Niles Red or Blue or whatever it's called? Yeah, because then somebody was telling me that I guess Nile Red had made one of these tellurium compounds that was like allegedly. Yeah, and then so he was like disputing the claim. Now I don't know if I could find the story, but basically these elements are supposed to get so smelly that they were like distilling a tellurium compound in Germany, I think is the story, and it caused like an entire town to be evacuated. But now I don't know. According to Niles Reddy, like made this compound and like was not as smelly as it like allegedly was. So I don't know. I'll let y'all make the compound, and you can get back to me on how smelly or not it is. But yeah, all these compounds tend to be horrible or smelly. And then our last ones are our halogens. And then of course our halogens are super reactive. So halogens we'll leave off. So they're reactive. Oh, and again, just make sure we're being super explicit, all on the same page here. So our group 5 had 5 valence electrons, group 6, 6 valence electrons. So now we're at the halogens, so 7 valence electrons. And this starts to get into, well, like why are they so reactive? And it's because they're just one away from this noble gas configuration. And so they're super reactive. They want to react with everything. And so we can look at them. And so they get more kind of nasty. So this is liquid fluorine, of course, condensed at a low temperature. So fluorine is a gas. And then, so I personally have not worked with fluorine. I've seen other people work with fluorine, and I can tell you I would not want to work with that. So fluorine has a special regulator. And so that's the other thing. So like gases that are toxic have this first of all, screw on backwards, so usually it's lefty loosey, righty tighty, but they're the opposite, so you know, like, hey, you're working with a really dangerous gas, but of course you need a special regulator that's hopefully corrosion resistant, but even then, fluorine is going to eat through everything eventually, and then of course you got to run these reactions in a fume hood, it's like super toxic, and those are pretty nasty reactions, so the group that I was familiar with, they were trying to fluorinate these compounds, but super nasty when they had to run those reactions. So same thing, chlorine is a gas as well. So usually you can like generate chlorine if you needed chlorine for a reaction. And then bromine is much friendlier. So like we mentioned, bromine is one of the few liquid reagents. So let's highlight liquids again. So right, not too many substances are a liquid naturally, but bromine is one of them. And so bromine is used a lot in synthesis because now it is a halogen that's easier to play with. It is a fuming angry liquid, but you can still pipette it. You can still draw it out with a syringe if you need to. So bromine, right, it's workable. You can use it. It's nice. It's a reddish-brown liquid. So like I said, it's usually a fuming, angry, reddish-brown liquid. You'd want to use it in a fume hood too, of course, because again, you don't want to breathe in all this toxic bromine gas and like halogenate yourself. And then iodine is another wonderful substance to work with as well. So I really like iodine. Actually, I think it's one of the prettier elements. So it's like this like violety, shiny, dark color. Really good, of course, in synthesis as well because it's a powder. And then, oh, what do you know? It's used in meth. So it's also a regulated substance. So it's, and it goes back to like meth is super trivial to make. And so like you just put an iodine group in there and then substitute it out, methylate it, not a big deal. But I mean, so many things are a precursor to meth. So I don't think that's really fair. So those are the halogens. All right, so that's a good place to kind of stop, right? So we're just kind of trying to understand our properties. So we're kind of just getting a taste of them. And then Wednesday, we'll go back and we'll start looking at that electronic structure again. So we'll look at it in detail, kind of again, like why is it that way? And then I'll try to work to hopefully get the My Open Math stuff going. I was a little slow, like I said, to reprogram. And then quiz this week on chapter 1 stuff in class. Or like I said, you're taking care of it online. Trying to think of anything else. Yeah. Well, I didn't put it on Blackboard. I didn't know if anybody wanted that. So I was just thinking, like, for the in-person people, if they could do My Open Math or paper. But if you really wanted to do Blackboard, I guess I could open it up. Yeah, yeah. If you took the My Open Math quiz, then that can be, like, your quiz grade. Yeah. So I saw that people were doing that, and I was trying to enter in the grades. You can double check me that I got it right. And then, oh yeah, I do have homework, so people wanted homework back. Otherwise, I'll probably get y'all in lab, especially because I don't know people's names. And I didn't finish grading labs yet, so I'm just kind of behind already.
I have to run to my biology class, but after that, if you want help with AI stuff, I can help you.
Okay.